Good evening, everybody. Yes, this is only a short talk. It's going to be less than an hour and a half, I promise. And you'll understand Tri-Band, and maybe you'll understand Tribulations by the time I've finished. So I'm going to be talking a little bit about color imaging in color, and what filters you can use to help your color imaging of astronomical objects. So I'll be talking a bit about cameras and then about the sources of light we're talking about, looking at the color in stars, galaxies, and nebulae, but also, more relevant, the interference from light pollution, which might be sodium streetlights or mercury streetlights, or these days perhaps LED streetlights. Then I'll be looking at filters that we can use, and I'll finish with just an example of what difference a filter can make to your astrophotography. So I'm talking about how digital cameras take color images. That might be a color DSLR camera, for instance, or it could be an astro camera. And specifically, we're talking about not the mono cameras that use external filters to obtain color images, but the so-called OFC, the so-called one-shot color cameras. So what I'm saying applies equally to DSLRs or one-shot color cameras. So what's going on inside? There were no external filters to give us color images, but all the filters are internal. If we look at the chip that actually does the imaging, if we were to look in enough detail, we'd see that each pixel is covered with a colored filter, red or green or blue, and hence we get a whole load of red information, green information, and blue information whenever we take a single color image of our dog, our cat, our family, whatever, using either the phone or whichever camera we choose to use. And each of those filters, of course, lets through a small part of the spectrum. There's the spectrum at the top there. And not surprisingly, the blue filter, the green filter, and the red filter let through the various chunks of the electromagnetic spectrum to give us a color image. Now, we know that lots of astronomical objects that are up there are beautifully colorful. Perhaps not so much galaxies. They tend to be a little bit beige. But there are loads of interesting objects up there. For instance, the beautiful red of the Rosette galaxy, or the blues and the lilacs of the Trifid Nebula. Sorry, the Rosette Nebula, the Trifid Nebula, the yellows and blues of Rho Ophiuchus, and the reds and cyans of the Veil Nebula, for instance. So we know those colors are up there. Unfortunately, the color receptors of the human eye don't make it easy to see all of these things. Our eyes simply do not work in color at low light levels. Even with the biggest telescope, the biggest light bucket you can find, you tend not to see any color in any of these objects. But the color is there, and we can catch them with a color camera. The catch is that whenever we try and take color images with a color camera, we are fighting light pollution. Just about anywhere. Okay, definitely in Birmingham and Liverpool and Manchester and London and pretty much near any town or city, you're going to be fighting light pollution. Maybe in the middle of the Pyrenees it's not too bad, but anywhere else we have light pollution. A lot of it is street lights that make sure that we know where to walk at night, but some of it is not necessarily practical, not always like that, but some people think it's a good idea to put street lights up everywhere. And the question is, what do we do about light pollution if we want to do astrophotography? Well, these days, software is fantastic. Software can do an awful lot. If we take a digital image, we're no longer talking about using film, and whatever you get, and that's the end of the story. With digital images, we can do a lot of processing with a computer. For instance, on the left there's a raw image of the North America Nebula with plenty of light pollution, taken from a sort of suburban environment. And we can see that even if the sky looks dark, when we take an image, we realize it's not as dark as we thought it was. The camera will pick up any light pollution that's there. But we can go from the left to the right with enough bits of software to help us along the way. We can process the image to tease out all of the detail in the nebula and hopefully get the sky close to what we think the sky ought to be if there wasn't any light pollution. So we can bring out the detail. Software can mitigate light pollution, as long as it's not too bad. If the light pollution is terrible, then maybe software has its limitations. But even then, you might say to yourself, well, why should I use software to get rid of light pollution? I don't like the idea of sitting in front of a computer and using a bit of software to try and get rid of the light pollution in my beautiful color images. can't we just not have it in the first place? We can't get rid of light pollution unless you want to move into the middle of the Atlantic, but maybe is it not possible to do something optically? Rather than try and correct for it after you've taken the image, is it possible to use filters to reduce the amount of light pollution so that what I catch is a little bit closer to the truth to make it easier to then process my image and get a nice color image of my target? So, can you use filters? Well, in principle, yes, but if you ask, well, what exactly do they do? When you say a light pollution filter, what is it actually doing? And the answer is, well, it depends which light pollution filter you're talking about. And the only way we can understand what effect these have is to consider briefly the nature of the light that we are trying to catch. In a sense, we're trying to catch the light from these distant objects, and we're trying to reject the light from these local sources of light pollution. So let's remind ourselves what it is we are trying to catch. If there's lots of stars, and let's for the moment just assume that a galaxy is just lots of stars. I know galaxies are more than just stars, but for our purposes, galaxies is just a large number of stars in the same region of the sky. Stars and galaxies emit across the whole spectrum. So yes, some red stars will be brighter in the red than they are in the blue. And some blue stars will be brighter in the blue than they are in the red. By the time you've averaged over lots of stars in an entire galaxy, the whole thing is basically lit up. The entire spectrum, all the colors of the rainbow coming from stars and galaxies. But it's different if you look at nebulae. Nebulae are clouds of usually hydrogen or oxygen and maybe a few other elements, basically large clouds comprising atoms, each of which is emitting characteristic set of colors. When you heat up a cloud of hydrogen, it glows with particular colors. And so in other words, the spectrum is not a continuous band of colors, it's very specific colors. Hydrogen, when you excite hydrogen atoms, they glow red and blue as well and other colors. And when you excite oxygen, it glows with a particular color. So, for instance, a lot of nebulae are made of hydrogen and oxygen, and so a lot of nebulae emit in the red and in the light blue or cyan. So that's one thing to bear in mind. Stars and galaxies are not the same as nebula. They have completely different color spectra, and they emit completely different colors. What about the light pollution we're trying to deal with? Again, that depends on what type of streetlights you have outside your house. Sodium streetlights, for instance, emit very strongly in the yellow. This perhaps might not indicate quite how strongly, but yellow is a very bright line in sodium, and there are some other colors as well. Similarly, mercury streetlights have a very strong green and a few other colors as well. But of course, sodium and mercury streetlights are now being replaced with LED streetlights. And LEDs emit across the entire visible spectrum. And therefore, we would have to treat these differently. If we want to get rid of sodium or mercury streetlights from our images, we have to take a completely different approach than if we want to get rid of LEDs. So that's one thing to bear in mind. Now we've got an idea of the colors of the objects we're trying to capture and the colors of the objects that are getting in our way because they're lighting up the sky, stopping us taking nice color images. So what sort of filters might help us to actually separate the wheat from the chaff, to allow us to see these beautiful objects in the night sky without getting completely overwhelmed by the light pollution? How many different filters are there that will do the job? I wasn't sure when I put this talk together, so I thought I will have a look. So I looked at magazines and I looked on the internet to find how many different filters I could find that would help mitigate light pollution. I found approximately 50. 50. Don't bother reading all the detail, but there were 30 different manufacturers from A to Z. Alta Astro at the top, ZWO at the bottom. 30 different manufacturers, many of whom produce more than one filter, and I'm going to tell you shortly what these various types of filter are all about. But you can see very quickly it's very confusing because it's not obvious whether these filters do the same job or not. They all have, a lot of them have silly names. Orion decided to call their filters the Ultra Block, yeah. And Teleview call theirs the Nebustar. But knowing what they're called does not help you understand what the filters are actually doing. And what I'm going to do here is to try and give you an indication by demonstrating to you the effect of a handful of filters. Some of them I found for myself, but a lot of them I borrowed from Sue and Rob, who happened to have a few, so I raided their observatory when they weren't looking and nicked a lot of their filters in order to try and figure out what do these filters actually do. So what I'm going to do now is switch on a light source, and this light source is an LED light source, so it's emitting across the whole of the spectrum. And what we're going to do is to have a look at the spectrum from this LED light source, and one by one, if I can avoid getting my sticky fingers all over it, I am going to put a filter in front of the light source, and what's going to happen is that that filter is going to block some of these colors. Notice that the filter doesn't cover the entire slit. So the top and bottom of the slit is still going to produce the complete spectrum. That's going to be there at the top and the bottom so that you have a reference, if you like. But the middle part of the spectrum, the light is going to come through the filter, and some colors will be transmitted through the filter, and some colors will be blocked by the filter. And so what's going to happen now is my assistants are going to circulate a couple of boxes. If you take that over to Sue. Yep. And each of you is going to get a diffraction grating so we can actually have a look at these spectra. So if you'd like to pass them out, thank you. For the benefit of anybody watching a video rather than watching this live, I'll now just recap what we were just looking at. The first thing we looked at was a dual band filter. And when that dual band filter came in, we should have been left with just the red and just the cyan. And that is the so-called H-alpha. I'm not going to explain why we call it alpha. It's just one of the lines that are produced by hydrogen when it glows, and the cyan color comes from oxygen. Remember this little cartoon I showed a couple of slides ago? Basically, any nebula that contains hydrogen and oxygen will have a spectrum with a red line and a cyan line and maybe other things as well. And so a filter that only lets through that and that effectively will let through all the light of the nebula, but will kill everything else. It'll kill moonlight, it'll kill twilight, it'll kill streetlights, but the nebula will just be as bright as ever. That's the idea of these particular filters. When we switch to tri-band, the name of this particular talk, I've called it tri-band simply because I chose to buy one of these tri-band filters. Tri-band looks very similar, but remember we noticed that the blue was much wider. That's because we're now looking at the region in which hydrogen emits in red, but hydrogen also kicks out some blue as well. When you look at atoms and electrons jumping around in atoms, electrons can jump between different energy levels and give rise to different colors of light. So hydrogen actually emits in the red and sometimes in the blue as well. And there's oxygen in this sort of cyany color. So a tri-band filter lets through all three of those. What about a quad-band filter? Obviously it lets through 4 of something, but it's not necessarily obvious exactly what it does. So let's have a look at a quad-band filter. This is about the same, but notice the red is now not as narrow as it was before. Now we're getting hydrogen and hydrogen again, but what's been added on the left-hand side is sulfur. That might sound a bit weird, but actually, yes, a lot of nebula do contain hydrogen and oxygen, and a fair number of them contain a bit of sulfur as well. And a lot of the images you see taken by the Hubble Space Telescope have been imaged in the wavelengths of hydrogen and oxygen and sulfur, and assigning colors to those 3 particular lines gives you the wonderful Hubble images that we all know and love. The catch for us is, if we're using a color camera to take this picture, it might catch emission from sulfur and emission from hydrogen, but they're both red. So we can't actually tell them apart. We take a color picture, the cyan and the blue tell us how much oxygen, how much hydrogen beta are we looking at, but over here we can't really distinguish the sulfur from the hydrogen. So it will collect more light from the nebula, but we won't be able to separate those particular elements because they will both look the same in our color image. What about other filters? This is where I came to raid Sue and Rob. So Sue had a Thousand Oaks filter, and it didn't say what it was. It simply said it was made by Thousand Oaks, the company. And the question is, if you buy a Thousand Oaks filter, how can you tell what it does if it doesn't say so on the side of the filter? So we put that up and took the spectrum of it, and it turns out to be that. In other words, it's letting through hydrogen and oxygen and H beta. It's actually a tri-band filter, but they don't call it that. It's not very helpful because they simply call it a contrast filter or something like that. So yes, it will improve the contrast of nebula, but it doesn't actually tell you which colors it's letting through and which colors it's blocking. Turns out it's a tri-band filter. What about UHC filters? UHC is a common acronym simply meaning ultra high contrast, which generally means is if you want to see a nebula, if you want to improve the contrast, you'll never make the nebula brighter, but if you've got a particular nebula of a particular brightness, if you make the sky darker, then perhaps you can improve the contrast of the nebula to the sky, making it easier to see or possibly easier to photograph. So ultra-high contrast should somehow make nebula easier to see. Let's see what it actually does. Well, this particular one seems to have our favorite cyan color and no red. So it's actually doing one thing and one thing only. It's letting through oxygen and killing everything else. So as long as your nebula is glowing like Billy-O in the oxygen, that's fine. If your nebula is all hydrogen and doesn't have any oxygen, that is not going to do you any good whatsoever. That's just going to kill the nebula along with the light pollution. So this is fantastic for the Veil Nebula, because the Veil Nebula has a huge amount of oxygen in it. It glows cyan, and therefore this filter would do well. But bear in mind, if you try it on another nebula, it might be next to useless. Another filter, this time one of Rob's, he had a CLS filter. What does CLS stand for? City Light Suppression. In other words, if you've got very bad light pollution, this ought to be good for you, they say. So what does a CLS filter do? Let's have a look at that. Well, it does something similar, but it obviously lets through quite a broad range of light, not quite the very end of the violet. It lets through quite a broad range of red, but basically it kills everything in the orangey bit of the spectrum. Remember, that's where sodium streetlights are. A lot of mercury streetlights are in that ballpark as well. So they call it city light suppression because it takes out a huge chunk of the spectrum, not the whole spectrum, but quite a large chunk of it, and that chunk of spectrum is usually where streetlights are, except for LEDs, which are across the whole spectrum. So it will be not particularly useful against LEDs. It will indeed be useful against mercury and sodium streetlights. So there again, we have the sulfur, the hydrogen, the oxygen, the H beta. All of those are present, and the big black area is nothing to do with the lines that we want to get from our distant nebula. Another one of Rob's, a BARDA contrast filter. Again, a contrast filter presumably lets through all of the nebula emission, hydrogen, oxygen, but darkens the sky to make the contrast better. So what does that look like? This is a little different. This is virtually the whole spectrum, except for it is quite definitely taking out sodium in the yellow. Okay, it's lost a bit of violet as well, but violet doesn't tend to make much difference in terms of streetlights, and there's no interesting emission from the nebula up there either. But this particular filter is letting through pretty much everything from red to blue, but it's taking a very heavy toll on sodium. Notice also there's a little bit of faint lines there, which means it's reducing the amount of mercury. If you've got mercury streetlights, then they will be dimmed a little bit, but they're not going to get rid of the mercury streetlights. Luckily, there aren't many mercury streetlights left in the UK. A lot of them have already been replaced. But this will be very effective against sodium streetlights. Against LED, no use whatsoever, because it's going to let through all of the lights from the LED streetlights. So against sodium, very effective. Against anything else, not so much. And finally, the one I showed at the end of the demo I've just given, the Hoyer filter, a photographic filter supposedly for taking pictures of the sky to improve the color rendition of the sky if you happen to live in light polluted areas. So again, what is it actually doing? Similar to the BARDA filter, it's letting through the entire spectrum except for the sodium around the sort of orangey yellow, maybe a touch into the green as well. You might not even be able to see it, but there's a very faint reduction of the amount coming from mercury. But essentially, this is a sodium filter. It only works on sodium streetlights. If you look at the blurb, it says this will work against light pollution. If you read 3 paragraphs down their webpage describing the filter, eventually you'll see this won't work on all streetlights. But it doesn't say, so many streetlights are now LEDs, this is going to be useless. Of course they're not going to say that because they won't sell any filters. But it's something that you've got to watch. Whenever they say this is good for light pollution, you've always got to ask yourself, yeah, but which type of light pollution is it good for? So those are all the spectra we've just been looking at, the unfiltered ones at the top and the bottom, just for reference, and these various ways that it could, in principle, let through light. Notice they're all different. There's, 8 different filters there, and none of them are actually the same spectral response. They all block or let through a different pattern of light. All of them are trying to let through either hydrogen or oxygen or both or other combinations. And they are all somehow trying to get rid of the light in the middle there. They're all trying to do something against the yellow, because traditionally that's where most streetlights were, in the yellow. Things are now changing. But if we ask ourselves, okay, there are apparently at least 7 different types of ways in which you can reduce light pollution, how does that map onto this ridiculous chart here? By the way, I have this printed out. If anybody is interested, well, I've got this particular nebula filter or contrast filter or whatever it is. Where does that fit in the grand scheme of things? I've got these printed out if anybody wants to check their own filters to see where they fit in the grand scheme of things. So I've already said that the naming convention is confusing because ultra block doesn't tell you anything about what the filter actually does. Nebustar doesn't tell you anything. Low glow doesn't tell you what happens other than it presumably gets rid of sky glow. Not only that, but the term that I've just described, ultra high contrast, you think, well, at least ultra high contrast is a type of filter. But no, look at all the ultra-high contrast there. Everybody uses that particular label. There's 10 of them there, but they use it in different ways. In some cases, an ultra-high contrast filter just lets through hydrogen and oxygen. It's a dual-band filter. But for other people, it's a tri-band filter. For other people, it's a sodium filter. So in other words, the ultra-high contrast is essentially meaningless. It might improve your imaging, or your ability to see a particular object in the night sky, but that depends on the object, and it depends on your streetlights. So UHC, in that sense, is meaningless. And you could argue that city light suppression is not quite so meaningless, but again, you can't rely on the name to tell you what that filter is actually doing. So let me try and visually summarize what I've been saying. The targets we might be interested in is stars and galaxies, which emit across the whole of the visible spectrum, whereas nebula emit only at specific colors, for instance, red, cyan, maybe others. And the streetlights, of course, we have sodium, which is pouring out lots of orangey yellow light into the sky, and LEDs, which unfortunately are pouring out across the entire visible spectrum. So if we decided to go with light pollution filters that are designed to work against sodium streetlights, not surprisingly, they work fantastic if you've got sodium streetlights. And it doesn't matter whether you're dealing with stars and galaxies or whether you're dealing with nebula. If you're plagued by sodium streetlights, then a sodium filter will work wonders. But they are next to useless if you happen to have LED streetlights, because they will only be taking out the yellow and they'll be letting the entire rest of the visible spectrum through, so you will still get 90-something% of the sky glow that you had before, even if you used these filters. And if we think about dual band or tri-band or quad band, you can bunch them all together because they're all doing the same thing. They're trying to let through only the colors that are coming from nebulae. They are restricting the amount of light that's transmitted only to the interesting bits that nebulae emit, the red and the cyan. So if you get yourself a dual or tri or quad filter, I bought myself a tri-band filter thinking this is going to be great. Of course, it's great for nebulae because it is letting through the light that nebula emit and effectively killing everything else. So it'll kill the moon, it'll kill twilight, it'll kill streetlights, it'll just give you the nebula and a little bit of background as well. And there's no point in using those filters for anything else. So in principle, they will reduce the sodium and they will reduce the LED, but they'll reduce the stars and the galaxy as well in brightness. So what's the point of reducing the sky glow from sodium or LED streetlights by a factor of 10 if all you're going to do is reduce the brightness of the galaxy by a factor of 10. You're not winning anything. The brightness of the galaxy relative to the sky glow is still going to be the same. They're both going to be dimmer. So there's no point in using these particular filters when you're trying to get a picture of a galaxy, for instance. So the bottom line is, if you've got sodium streetlights, you'll be able to find yourself a filter that works nicely. If you're interested in nebulae, you'll be able to find yourself a filter that works nicely. But this top right box, if the object you want to image emits across the entire spectrum, and your streetlights are emitting across the entire spectrum, there is nothing you can do about that with filters, because there is essentially no difference between the galaxy you're trying to image and the LED streetlight that's interfering with your ability to image. They're both emitting over all colors, so filters will not work. All you can do is to say, well, I've got to go back into Neanderthal mode, sit in front of a laptop and do the processing that will get rid of the sky glow and allow me to see the objects that I'm interested in. So as I say, I bought myself a tri-band filter because I wanted to give this a go just to see, well, do they actually make that much of a difference? Tri-band has the advantage that A, it reduces light pollution for the reasons I've just gone through in the last 10 minutes. It will also get rid of scattering from the moon, because that's effectively just light at all wavelengths. It will get rid of twilight, because that's mainly at the blue end of the spectrum. But also, one thing I thought was quite interesting is it will generally make the stars a little bit dimmer. Stars are emitting across all colors. So if we only let through the colors of a nebula, then the stars will be a little bit dimmer. And quite often, when you're trying to photograph a nebula, for instance, in the middle of the Milky Way, you find there are so many stars, they tend to completely crowd out the rather interesting nebula that's sitting there behind all of those stars. So a tri-band filter will allow you to make the stars a little bit dimmer. The nebula will be no brighter, but the stars and the sky glow from light pollution will be darker. And if there was any moon, that sky glow will be darker as well. So hopefully you'll be able to see the nebula more clearly. So there's no point in using a tri-band filter on the galaxy. The galaxy is just all colors. There's no point in doing any filtering on that if you've got an LED streetlight close to you. But with an object like the Veil Nebula, which is emitting, the red is hydrogen, the cyan is oxygen, so this is effectively just hydrogen and oxygen. So in principle, a dual band or a tri-band or a quad band filter might be very effective. That's the picture I took with my Nikon in 2019 at the Star Party, back in 2019 at Ledbury, a nice dark sky site, so essentially no light pollution to speak of, and it gave me this image, and the main problem, this is an image with no filter, and the main problem is there were so many stars, even by trying to process it with software, I found it very difficult to suppress those stars to bring out the detail that I figured was possibly present in the nebula. You can clearly see the western and the eastern veil, and it's a little bit difficult to see any other structure in there just because there are too many stars. So I tried rephotographing this one from a different site, not a dark sky site. I tried to do it from outside my front door. And outside my front door, there's an LED streetlight closer to me than the back of the room is. So just a few meters away from my front door, there's an LED streetlight. But I did, with the same camera and the same lens, I put a tri-band filter on and imaged the same thing. So this is taken in 2022, close to an LED streetlight, and the moon was up with a tri-band filter, and I was then able to see much more detail simply because the stars don't get in the way. And therefore, it is possible to see detail in the structure here. The exposures were comparable, so I wasn't imaging for longer in order to see anything more. I was just imaging in such a way the stars did not dominate the field, and hence I was able to see detail, for instance, in Pickering's triangle there, which was very difficult to see when there were just too many stars for me to deal with. So a tri-band filter does work under light-polluted skies. Software has its place, and software can always help when it comes to image processing. But if you're in light-polluted skies, then a tri-band filter or something similar will allow you to cut through the light pollution and cut through the moon glow and get some nice images. There's the same image, but because we've managed to suppress the stars, we can now play tricks, if we so wish, on saying, well, the stars are here and you can just about make out the nebula. This might be just about what you would see of the nebula through a very big telescope, for instance. But because we've now suppressed the stars, it's easy just to say, well, in software, let's just make the stars a little brighter. Or, no, let's leave the stars where they are. Let's just make the nebula a little brighter. Or a bit brighter still. Yeah, maybe a bit more. Yeah, okay. So we can play tricks with the software once we've got to a point where we can see the detail in the nebula without the stars completely washing out that detail. And of course, we can always play tricks with software and say, well, it's very nice, but why don't we take the stars out completely? Okay, that's nice. Now we can definitely see there's far more in this supernova remnant than we could possibly see in the original image from a dark sky site without a tri-band filter. So it's been a little bit of tribulations trying to make an image that works nicely for the veil. I haven't yet taken enough images of an object with a tri-band filter and without a tri-band filter just to make that comparison. This is the only comparison that's sort of direct in terms of actually making that direct comparison. But I think I've convinced you that tri-band filters have their place. Software has its place, tri-band filters and other dual band or quad band filters have their place, but be wary of anything that claims to be a light pollution filter. Remember, a light pollution filter will not necessarily work for your street lights. It depends on what you've got in your neighborhood. Thank you all for listening.